Picture a region in space so intense and unforgiving that light itself cannot escape its grasp. A place where the known laws of physics reach their limits and our understanding of reality begins to unravel. These are black holes, enigmatic cosmic giants that fascinate scientists and stargazers alike. Today, we're taking you on a journey into one of the most mysterious phenomena in our universe, inside a black hole. The notion of an ultra-compact object with gravity strong enough to trap light isn't new. In fact, it dates back to the late 18th century with thinkers like Jean Michel and Pierre-Simon Laplace, who wondered about dark stars. But the true revolution arrived in 1915, when Albert Einstein published his theory of general relativity. This new approach to gravity, viewing it as the curvature of space-time, hinted at something even more extreme. Only a year later, Karl Schwarzschild uncovered a solution to Einstein's equations that described a spherical region from which nothing could escape. While this result was mathematically intriguing, many scientists of the time doubted such an object could be real. It would take the work of Subrahmanyan Chandrasekhar, Robert Oppenheimer, and John Wheeler in the mid-20th century to show that certain stars could indeed collapse into ultra-dense states. Wheeler also coined the evocative term black hole, capturing imaginations worldwide. Today, general relativity underpins our understanding of black holes. Matter tells space-time how to curve, and curved space-time tells matter how to move. If matter is dense enough, the curvature can become so steep that beyond a certain boundary, even light cannot escape. This boundary is the event horizon, and it marks the point of no return. So how do black holes form? Typically, it happens when a massive star dies. Throughout its life, a star fuses elements in its core, producing energy that balances its own immense gravity. When it runs out of fuel, often once it starts making iron, it can't support its weight anymore. The core collapses and the star's outer layers explode in a supernova. If what's left of the core is massive enough, roughly 3 times the mass of our Sun or greater, no known force can stop its collapse, and a black hole is born. In this case, all of that stellar matter shrinks down, creating a region of extraordinary density. That's a stellar mass black hole, typically just a few kilometers across. But there's another class of black hole out there, the supermassive kind lurking in the centers of galaxies, including our own Milky Way. These cosmic giants contain millions or even billions of solar masses. Scientists aren't entirely certain how they form. Perhaps they arise when colossal gas clouds collapse directly in the early universe, or perhaps they grow from countless mergers of smaller black holes. Evidence suggests both processes may play a part. The phrase black hole might sound like a simple void, but there's more structure here than you might think. First is the event horizon, the boundary separating the black hole's interior from the rest of the universe. For a non-rotating black hole, known as a Schwarzschild black hole, this boundary is called the Schwarzschild radius. But in reality, many black holes spin rapidly, following what physicists call the Kerr solution. Spinning black holes exhibit frame-dragging effects, twisting space-time around them. Outside the horizon, swirling around the black hole, you often find an accretion disk, hot, ionized gas spiraling in at tremendous speeds. Friction and gravity heat this material to such extreme temperatures that it radiates intensely, often in the X-ray part of the spectrum. Sometimes, spinning black holes produce powerful jets, streams of charged particles that blast out from the poles at nearly the speed of light. These jets can stretch thousands of light years, showcasing the black hole's far-reaching influence. At the very center is what theory calls the singularity, where space-time curvature becomes infinite. But that's just the mathematical description. Physicists suspect that a more complete quantum theory of gravity might replace that infinite point with a different structure. For now, the singularity remains a realm where our current models of physics break down. What if you ventured too close to a black hole? Once you cross the event horizon, there's no turning back. An outside observer would see your clock slow down and your image redshift, fading into darkness near the horizon. From your own perspective, though, you'd pass the horizon without noticing an immediate jolt, especially if the black hole is supermassive and the tidal forces at the horizon are not extreme. Deeper in, things get far more violent. Tidal forces can stretch you like spaghetti, an effect called spaghettification. Every path you take inevitably leads closer to the center, and there's no possible way to communicate back to the outside world once you're inside. At the Singularity, the gravitational pull skyrockets. Classical general relativity tells us that density and space-time curvature become infinite, which suggests a breakdown in the equations. Here we need a quantum theory of gravity to see how matter, energy, and space-time might behave under these extreme conditions. Some researchers propose that the singularity could be replaced by a finite, ultra-dense core, while others imagine exotic phenomena like Planck stars that bounce rather than collapse infinitely. None of these ideas, however, have been experimentally proven, mainly because the nature of black holes inherently shields direct observation of their interiors. For much of their conceptual history, black holes were theoretical oddities. But in the last few decades, observational evidence has mounted galactic centers. By tracking the orbits of stars near the Milky Way's center, astronomers demonstrated that a 4 million solar mass black hole, known as Sagittarius A, lurks there. High-energy light. Space telescopes like Chandra detect intense X-ray sources, often tied to hot accretion disks spinning around black holes. Gravitational lensing. Black holes can bend light from background objects. In some cases, this warping creates arcs, or multiple images that confirm the black hole's mass and location. One of the greatest achievements in recent times has been the direct imaging of a black hole's shadow by the Event Horizon Telescope, EHT. In 2019, the world saw the first image of the supermassive black hole at the center of galaxy M87. Rather than a traditional photo, this was a radio-based image combining data from multiple observatories around the globe, creating a virtual Earth-sized telescope. The picture revealed a dark core, where the black hole's silhouette blocks the background light, surrounded by a bright ring of superheated plasma. It was direct confirmation that space bends in exactly the way general relativity predicts. In 2022, the EHT also released an image of our own Sagittarius A star, giving us a closer glimpse of the complex environment in our galactic core. Another game changer arrived in 2015 when the Laser Interferometer Gravitational Wave Observatory, or LIGO, detected gravitational waves for the first time. These ripples in spacetime were generated by the merger of two stellar mass black holes over 1 billion light-years away. It was a historic moment that validated a major prediction of Einstein's theory. Since then, LIGO and its partner experiments Virgo and KAGRA have identified many more black hole collisions. These signals tell us how massive the black holes were, how fast they spun, and even how far away they merged. This new form of astronomy, often called multi-messenger astronomy, when combined with electromagnetic observations, lets us study black holes in ways previously unimaginable. In the 1970s, Stephen Hawking proposed that black holes aren't truly black. Instead, quantum fluctuations at the horizon might allow some particles to escape, an effect now known as Hawking radiation. Over vast timescales, this process would cause the black hole to lose mass and eventually evaporate. But there's a catch. If a black hole evaporates fully, what happens to the information carried by the particles that fell in? Quantum mechanics insists that information can't be destroyed, but classical black hole theory seems to suggest that it is. This black hole information paradox remains a hotly debated topic. driving physicists to consider new theories of quantum gravity or novel ideas about how information may be encoded on the event horizon itself. Black holes don't just consume matter, they influence the evolution of their host galaxies. Supermassive black holes can spark energetic outflows, or jets that heat, or even drive away gas, regulating star formation in the galactic disk. Observations of quasars, hyperluminous galactic centers, reveal that such feedback can shape the destiny of entire galaxies, curtailing or triggering bursts of starbirth. Galaxy collisions often lead to the merging of their central black holes, forming binary black hole systems that eventually spiral together, releasing powerful gravitational waves. These events are fundamental to the tapestry of cosmic evolution. By studying them, astronomers piece together how galaxies grow, merge, and sometimes feed their resident black holes. Despite our progress, there's still much to learn. How do supermassive black holes form so quickly in the early universe, when it was less than 1 billion years old? What really happens at the Singularity? Do intermediate mass black holes fill in the gap between stellar and supermassive types? Coming missions and technologies promise more answers. The EHT may expand its network for better resolution, potentially showing us the dynamic behavior of matter swirling around the event horizon. Space-based gravitational wave observatories, like LISA, the Laser Interferometer Space Antenna, will detect the lower frequency waves emitted by supermassive black hole mergers. Meanwhile, advanced X-ray telescopes will probe closer to the black hole's edge, helping us understand the physics of accretion disks and relativistic jets. Black holes remind us that reality can be far stranger than our everyday intuition suggests. From the moment a star collapses into a singularity to the grand-scale jets that can shape entire galaxies, these cosmic behemoths weave themselves into the fabric of our universe. They challenge us to unify Einstein's geometric vision of gravity with the quantum mechanics that govern the subatomic realm. We've come a long way, from the first theoretical solutions to the direct imaging of black hole shadows, to the detection of gravitational waves produced by colliding black holes. Yet we still stand on the cusp of discovery, with many questions unanswered. As we refine our instruments and deepen our theoretical insights, black holes will undoubtedly continue to push the boundaries of science and possibly reveal new secrets about the nature of space, time, and the universe itself. Thank you for watching. If you enjoyed this journey through the extreme realm of black holes, don't forget to like, share, and subscribe for more cosmic mysteries. Until next time, keep exploring and remember that reality is often more astonishing than we ever imagined.